All right, today we're going to finish up section 9.4, which is permutations and combinations. When we talked about permutations, one of the things that we really focused on was the fact that when you're calculating a permutation, it's because the order of something matters. Either it matters because it says how many different orderings, that's kind of a key phrase, or it's distinguishably different. So we had gotten to an example last time where we talked about people winning different amounts because there were actually 3 different prizes. So it mattered in which order they pulled things out of the hat, so to speak. There are scenarios where the order doesn't matter, where it doesn't matter if you're pulled out first or you're pulled out last of these 3 winners, you all win the same thing. And when that happens, we have something called a combination. So a combination looks very similar in its formula to a permutation. So compare this, go and write it down, and then compare this to the formula we looked at last time. And if you can, tell me, what do you notice is different? It's got a C in it. Yeah, that's just notationally, right? Combination versus permutation. Yeah, good job. So the part in the formula that's different is that there is an R down here on the bottom, R factorial. So think with me. If you've got a value in the denominator that you didn't have before, and we're working with whole numbers here, right? Will the result of this whole thing be bigger or smaller than we had before? It's going to be smaller. I'm dividing by more stuff, right? Because all my numbers are positive numbers and they're all whole numbers, bigger than 0. So, and not fractions is what I meant to say. So as we're taking a look at this, combinations give me fewer outcomes, and that should make sense because I'm not concerned about the ordering anymore. It's the same thing if I get if I have the 3 of you winning, it's the same thing no matter what order it is you win in, right? So of course there should be a fewer value and fewer ways in which this happens. And if we take our scenario, this is our scenario last time, we had 3 people winning something, they all won different things. Now we're going to take the same thing, right? 30 contestants, 3 winners, but now it doesn't matter the order I select them in because they all win $75. Okay? So in this scenario, I do have a combination because the order doesn't matter. They're all winning the same stuff. So I have my 30. It's a combination, and I select 3 winners. So I have the same 30 factorial on top as I had before, and I have the same 30 minus 3 on bottom as I had before. But now I also have a 3 factorial on bottom. So, or you could jump to the fact that this is 30 factorial, 27 factorial, and 3 factorial. And when you do that, you should recognize that each of these 2 numbers add together to give you the numerator. That always happens. That's the way the formula works. So I solve this the same way I did last time, which means I write the 30 out until I can get it to cancel perfectly with something that's already in the denominator. So I have 30, 29, 28, and then I have that 27 factorial, right? Because I have that exactly in the denominator already. So I stop when I get to 27 factorial. And then remember, since the 3 factorial doesn't have exactly 3 factorial on top, I have to write out 3, 2, 1. So the 27 factorials are perfect matches, so they reduce. And everything else has to reduce by division like you would normally reduce with fractions. So I have 3. Well, 3 and 2 actually go into 30 pretty nicely. So that kind of works nice. It doesn't always work to go in the same number. Sometimes it does. 3 times 2 is 6. 30 divided by 6 is actually 5. So now we're going to multiply 5 times 29 times 28. And what is 5 times 29 times 28? Yeah, 4,000. Did you say 60? Good. 4,060 different ways that we can select these 3 winners when the order doesn't matter. Compared to 24,000 ways when the order didn't matter, right? It's considerably larger. All right, so I want to pause for just a second and kind of ask you if you can think about with me some places and things that you know of where order matters or where it doesn't. So can you think about some examples maybe of when you're selecting or talking about how many ways something can happen or order does or doesn't matter? Baking a cake, would the order matter?
Yeah.
It might. It depends, right? Like you wouldn't want to put the frosting inside the cake mix. So there might be components where the order matters, and there might be some components where it doesn't. Does it matter whether I put the eggs in or the sugar in first? Probably not. However, I will tell you that it might matter whether you put the butter in or the eggs in first. My sister put the butter in and then the eggs in and realized she was supposed to melt the butter, and she put it in the microwave. What happened? The eggs got cooked. That didn't work. So there might be components where it matters, right? There might, yeah. It's kind of how dressing yourself in the morning works too, right? There are components that have to go on before others. Just saying. Here's a scenario for you. What about if you had an election? There's two ways that an election could happen, and it depends on how the election is structured. If you were selecting like a president, a vice president, a treasurer, like if we were in this room and we were like, we need somebody who's going to be the president, somebody who's the vice president, and somebody who's the treasurer, and we need 3 people. It would matter, right? If we selected by popular vote. You know, the person who got the most votes is president, the person who got the second most votes is vice president, the person who got the third most is treasurer, right? That would be an order matters. But you could do an election where we're just creating a committee of people who's going to plan some sort of an event, and it doesn't matter who gets the first number of votes, the second number of votes, and the third number of votes, because you're just in a committee. Another scenario where it's kind of like that is a race. If you're running a race, most of the time, would you say that order matters on who finishes? Yeah, most of the time it does, right? First place person gets some sort of a prize that looks different than the third place person. But what about when you're doing the Olympics and they have all these different heats of people that are moving on to different rounds? Sometimes it doesn't matter if you finished first or you finished second, and people are actually really aware of that because they don't want to sort of go all out just yet. So it really does, there is context. It's not just that you can always say that something matters or something doesn't. You have to look at the context. So let's take a look at a few examples. I think I have a few more in here. This one is the phone numbers. It says if all the phone numbers in a large business are 405-767, you'll have that happen sometimes in a specific location. Like all of the OBU phone numbers are 405-585. Is it 585 or 858? I can never remember which one it is. It's one of the two. So yeah, this happens frequently. The question is, how many different phone numbers could you have then? So the first thing you need to find out is, does the order matter? Really? If I dial 1234 at the end, I don't get a different person than if I dial 4321? Oh yeah, I do. You've probably called somebody's wrong phone number like that before, right? Does the order matter? Yes, it does. It definitely matters what order you put those last 4 digits in. So since the order matters, is it a combination or a permutation? It is a permutation. So here, the order matters. So we have a permutation. Okay, perfect. Next, is it a permutation of like or unlike objects? Well, for the most part, we work with permutations of unlike objects. Those locations are not the same. It's kind of the same thing of like the Skittles in the bag, right? All of my numbers are distinguishably different, right? The 7 in no way, shape, or form looks like the 3. So this one, they're unlike objects, which means that our formula for a permutation is NPR, okay? What are N and R? Well, if you remember, N is the number that we have, the number of choices. And R is the number we are choosing. Oh, there's one more thing that I meant to say, and this will affect my information, and I forgot to mention it. When we talk about permutations, let me go back over here and write it on our slide. We can't have repeats. And the same thing for combinations. There's no repeats. And if you think about my examples, it should make sense, right? We don't have the opportunity for the same person to win 2 of the $75 gift cards, right? We don't repeat the same winner. But the problem is that when we're looking at these numbers, can I repeat numbers? I can. So this one doesn't end up actually being a permutation because my numbers repeat. Okay, so we don't end up with a permutation because of that. So what do we end up with? Well, we end up with something we saw at the very beginning last time. So if you flip to your very first page of notes, you will see this, the fundamental principle of counting. The fundamental principle of counting applies, it applies more broadly than what I'm about to say, but it definitely applies when numbers can repeat, when something can repeat itself. And that's what's happening in our scenario, is that the numbers can repeat themselves. So I have 4 locations for numbers at the end, right? There's 4 X's there at the end. And how many different digits could I put when I dial my, what is it, 3, 6, the 7th digit? How many different options could I put in for that first blank spot? It's more than 9. It's 10 because you have to remember the 0, right? I've got the digits from 0 to 9. I don't have a 10, but I have 0 to 9. How many different options when I dial the next number? Another 10 options. And the next one? And the next one. They're all 10 options. They're all of them have 10 choices. So what is 10 times 10 times 10 times 10? It's 10,000. There are 10,000 phone numbers that all start out 405767. Okay, let's take a look. We just still think through the problem the same way. A worship team. A worship team practices 8 songs on Wednesday night for the Sunday service. If the worship minister plans to choose only 5 of the 8 songs practiced, in how many ways could the songs occur? Okay, so does the order matter? Sure? Doesn't that phrase just say that it mattered? In how many ways could the songs occur? It does, right? It doesn't say how many different selections of 5 songs are available to pick from. It says how many ways could I play my 5 different songs. Not only that, but if you think real carefully about worship services that you've been in, do you think that the worship minister puts them in a specific order for a specific purpose? Absolutely. There's a flow, there's a cadence, there's keys, there's tempo, there's all of that that's considered, and it's different if you put it in a different way. So there's 2 sort of things playing out here that indicate that we do have something where the order matters, but it does matter. So if the order matters, and it does, we have 2 possibilities, as we discovered on the last thing, or last possibility. One possibility here is that we have a permutation. The other possibility is that I have the fundamental principle of counting. And the reality is either of these options will work on this because within a worship set, the songs aren't repeating, right? I don't sing the first song, and I sing the second song, then I go back and sing the first song, and then I sing the third song, and I go back and sing the second. That's not what's going on, right? We're selecting 5 songs, and we're going to play all of them. So if you do it as a permutation, you have 8 songs that you're selecting from, and you're selecting 5 of them. So it looks like this. So we'll come back to the fundamental principle of counting so you can see that one in a minute, but we're going to do the permutation option first. So, permutations. What goes on top? Look back at your formula if you need to. What is it? 8 factorial, right? Okay, good. What goes on bottom? Not quite. 8 minus 5. Yeah, 8 minus 5 factorial on bottom. And of course, 8 minus 5 is 3. So I'm going to write my 8 out. 8, 7, 6, 5, 4, until I get to 3 factorial. And what point they match, I can stop so that they will cancel, right? And then we need to multiply 8 times 7 all the way down to 4. And what do we get? There's 6,720 ways this could happen. Let's think about fundamental principle of counting, because it works really nicely on this one too. We have 5 songs we're selecting, correct? So we could think of it kind of like our 5 numbers in the phone number, or the 4 numbers that I had in my phone number on the last problem. How many options do I have when I play my first song? There are 8. But once I play it, I've used up that option. So how many options do I have now? 7, and then 6, 5, and 4. And I don't think you probably need to multiply them to recognize that those are the same digits you just multiplied before, right? So again, you get the 6,720 different ways from either perspective that you consider this problem. And the reason, again, that we could use permutations when we couldn't on the last one is because on the last one, we had to be able to repeat the digits. And here, I don't necessarily have to in fact, I don't repeat my numbers, right, or my songs. So since there's no repeating, I have a choice on which of those 2 options I would go with. All right, we're going to talk just a little bit about cards. And we've talked about cards before. Shake your head if you know what I'm talking about. Right? So we've talked about black and red and the suits and the how many cards of this, that, and the other. What we're going to talk about here, though, is what happens when we play a game. So think about what happens when somebody plays a game with you. I don't really even care if there's 5 cards or if there's 3 cards or there's however many cards you're dealt. Does the order in which you're dealt the cards matter at the beginning of the game? Sadie says no, and you're right, Sadie. Why does it not matter? Yeah, once you put them in your hand, in fact, that's probably what you do first, right, is you rearrange them in whatever order makes sense for the game you're playing. Right? I mean, from Old Maid to Go Fish to poker. It doesn't make any difference. Once they're in your hand, you rearrange to a specific order for whatever the game is. So, since the order does not matter, I don't mean in gameplay, right? Like obviously, as the game continues, the order in which cards play out on the the common ground or whatever, obviously those sorts of things affect. But the cards that you've already received don't matter. So, since the order does not matter, will I have a combination or a permutation? Yeah, so the order does not matter. So I have a combination. Okay, so if I'm handing out cards to everybody, and there's 52 cards in my deck, as it describes, and I'm creating a 5-card hand, how many different 5-card hands are possible? Well, we said that this is a combination. How many things do I have to choose from? 52. And how many am I choosing? 5. I only get 5 cards in my hand. Combination formula says 52 factorial on top. What is on bottom? Right, 52 minus 5 factorial, and then 5 factorial. Okay, I'm going to avoid writing this out a second time. What's 52 minus 5? 47. All right, so we're going to write our 52 out until I get to 47. So 52, 51, 50, 49, 48, and then 47 factorial will match the 47 factorial that's already down there. And then I have 5, 4, 3, 2, and 1. Okay, so my 47s are going to cancel. Now I'm going to let you guys tell me, what do you want to cancel next? There's so many ways we could do this. Somebody tell me one. Okay, Matt, I heard you first. The 50 with what? The 5. And so that will leave me with what? 10 on top. All right, what's next? Somebody give me another suggestion. The 4 and the 52. Okay, if I cancel 4 and 52, what am I going to get? 13 on top. That's right, yeah. What about next? The 3 and the 48. And if I cancel those, what am I going to get? 16. Now what? Lots of choices. 2 and the 10. Sure, why not? And I'll get a 5. Okay, if you choose different ones, it's going to be the same answer at the end. Doesn't make any difference. Just pick what you can, reduce things out, of course, correctly. But all the numbers, when reduced correctly, will result in the same product. So I have 13 times 51 times 5 times 49 times 16. Be careful to capture everything that's left when you multiply. How many different 5-card hands did you just come up with? Starts with a 2. I hope you're using a calculator, otherwise we're going to be at this for a long time. 2,598,000. Yep. There are 2,598,960 different 5-card hands. That's some crazy stuff, right? Really, that's like a lot. Okay, so the question becomes when you're playing a game like poker, and we're going to look at some different 5-card hands that come up in poker, and when they talk about likelihood of things, or if you've ever watched, my husband used to watch the Poker Channel. Do they still have that? Probably they do. And it would tell you the likelihood of somebody winning at different points in there and stuff like that. And then he would watch the ones where they played Texas Hold'em, I think, and it's still a 5-card hand you're looking at and how likely those things occur. And there's different chances and different payouts and who has the better hand and things like that. And the better hand is determined on which is less likely to happen. And so that's what we're going to look at, is which is less likely to happen. So this hand that we're looking at in Part B, Example 8, Part B, it says how many different 5-card hands contain all diamonds? Okay, so now I can't just pick any card. So it's still a combination because it still doesn't matter what order they're put into my hand in, right? But how many different options can I pick from if I'm supposed to have all diamonds when I'm done? Close. 13. Yeah, there are 13 diamonds, but I still need a 5-card hand. So this is 13, combination 5. Does that make sense to everyone? So I have 13 factorial on top, 13 minus 5 on bottom, factorial, and then 5 factorial. What is 13 minus 5? What is it? 8. 8's right, yeah. So we'll write our 13 out till I get to 8. So 13, 12, 11, 10, 9, 8 factorial, which will cancel with the 8 factorial, and then I have 5, 4, 3, 2, and 1. So of course the 8's go away. There's some actually really nice pairing that we could do on here if you want to, but you could also not. What would you like to reduce? Yeah, did you know I could do 5 and 2 and 10? How fun would that be? That'd be good, right? What else could I do? How about 4 and 3 and 12? Isn't that fun? And if you don't do it that way, it's fine. But I have 13, 11, and 9 that are left. And if I multiply those together, how many do I get? Okay, now if I had asked you a minute ago, is 1,287 different hands a lot? You probably would have said, yeah, I mean, that's 1,000 different hands. But if you compare that to the 2 million I just got on the previous slide, is that very many? Nope, not very many. Not only that, but on Part C, we could actually look at the probability of getting the 5-card hand that I just described, a 5-card hand of all diamonds. Well, there's a so we're going to have a probability of all diamonds. That's what we're calculating. So what do I need to get? Well, I need to get all diamonds, right? The number of ways of getting all diamonds divided by the number of ways of getting anything. So how many different ways can I get all diamonds? That was what I got from Part B, 1287. How many ways can I get just anything to happen? Yeah. Part A, 2,598,960. That's part A. So let's divide. What happens when I do 1287 divided by 2 million, da, 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 da? What'd you get, Beth Ann? Oh, you didn't yet. You just know it's going to be really tiny, huh? Okay. We'll go with 4 decimal places because you're going to need them.
0.0004 or 5 if you round it.
Yeah, 5 if you do your rounding, yeah. Yeah, that's pretty small, right? Even if you want to think like, well, what's that percentage? And you multiplied this by 100, that's a 0.05% chance. Probably not going to happen, right? It's very unlikely. Okay, I know we're not going to have time for group work, but we still should have time to finish our last 2 parts to our examples. So let's take a look at another problem that is similar to this one, but it involves committees instead of cards. All right, so we've got a committee that we're going to select. It's going to be a committee of 3 people. I'm sorry, are you okay, Kira? Summer?
Yeah, I was like, my time didn't keep showing up when we get that 5.
Does it have an E at the end?
Yeah.
We're going to change it when we get done. Check with me. You've got it in scientific notation right now. That's what's happening. Yeah. So if your number is not showing up at 0.0005 like this, that's what's probably going on. Okay. Committee of 3 people is selected at random. There are 7 seniors, 5 juniors, and 3 sophomores. So here's one of these sort of keyword kind of things. If we're selecting a committee, I mentioned this before. If it's a committee versus a president, vice president, treasurer, then the order doesn't matter. Everybody with me so far? Okay, we've got 3 people we're selecting for this committee. The first question wants to know, what is the probability the committee consists of all seniors? So how many seniors do I have? 7. The order doesn't matter, so it's a combination. And how many am I selecting? That's my next one, sorry. How many is on my committee? 3. I only want to pick 3 of them, and I want them to be all seniors. So this is 7 factorial on top. I think we can probably do the subtraction in our head. 7 minus 3 would be 4 factorial on bottom with a 3 factorial because I'm doing combinations. And if I multiply these out, 7, 6, 5, and then 4 factorial, which will cancel with my 4, and then 3, 2, and 1. The 4 factorials cancel, and 3 times 2 is 6 from the numerator. So what do I end up with? 35. There are 35 different committees that would be all seniors. But if I'm wanting to find, I'm going to skip some space down here, like I did on part C of the previous problem, the probability of all seniors, I would need the number of all senior committees, which I just found, divided by the number of any committee. Right? How many committee options are there? Well, I'm selecting 3 people, but how many am I having to select from if I'm selecting from any of the different classifications? 15. So how did you get 15? Okay, the 7, the 5, and the 3, right? Yeah. There are 15 I'm selecting from among. So I have actually 15 factorial on top. 15 minus 3 would be 12 factorial, and then the 3 factorial. So 15, 14, 13, 12 factorial. I have my 12, and then I have 3, 2, 1. So the 12 factorials cancel. I don't get to cancel this one quite so cleanly. The 3 will cancel with the 15 to give me 5, and the 2 will cancel with the 14 to give me 7. So I need 5 times 7 times 13. What is that? 455, right. So there are 35 committees of all seniors, 455 committees of just whatever. And what is 35 divided by 455? And we'll use 4 decimals again as well. I have 0.0769. Okay. All right, we're close, but yeah, 0.0769. All right, one tiny caveat on part. We'll just do this one really, really fast, I promise. This one says no seniors, probability of no seniors. So how many juniors and sophomores do I have to select from? 8. So I have 8C3. This is 8 factorial over 5 factorial, 3 factorial, 8, 7, 6, and 5 factorial. And then I have 3, 2, 1. Very, very similar, right? There's my 5 factorials. 2 and 3 is 6. What's 8 times 7? 56. And then I already calculated the number of, so this is the probability of no seniors. So the number of committees with no seniors, which is what I got from up here. And then I have the number of all committees. That's what I got on the part A before. So I have 56 over the 455. It's not a lot larger, but it's slightly larger. And it's 0.1231 for a probability. All right, I know that was like whirlwind at the end. Apologize for that. Group work, homework, all is homework, but still do it in order, right? Do the group work at the top and then the homework after. Make it easy on my grader, please. And then that will all be due on Monday. No class on Friday, okay? Have a great weekend.